Welcome. In this video, we're going to use technology to create graphs of the three functions you see here. So the square root of the absolute value of x, the cube root of x, and the absolute value of x minus x squared. We're going to clearly label and scale all of these, then identify all extrema based on these graphs. Okay, so as you can see here, I went ahead and opened up the GeoGebra Classic app. You can also do this in a web browser. And now I'm going to type in y equals the square root, now an absolute value, and x. And there it is. There's my graph of the absolute value of x. So please take a moment and sketch this on your own paper. If you're using technology, you can use a screenshot. Okay, so as you can see here, I have my sketch of y equals the square root of the absolute value of x. And when I say label and scale, I mean the numerical label should be clearly visible. I'm going to quickly trace over mine since everything is kind of small. So 1, 2, 3, and so on. So on your own paper, make sure things are clearly labeled and scaled, especially those of you in my classes. I'm going to be looking for these things when I grade your work. So I do see a lowest value, and that lowest value, I see it right here. There we are. That's a little easier to see now with just the scales and not such a thick axis. So the lowest value I see right here at the origin. And since it is the absolutely lowest, smallest y value, that is, a y value of 0 is the smallest as this goes, this is an absolute minimum. And so that absolute minimum of y equals 0 is located at the 0.00. And oftentimes you'll just see these identified by the x value. That is, you'll often see something like this written down in textbooks or in other videos, like absolute minimum at x equals 0. And all that's doing is identifying the location along the horizontal axis of x equals 0 here as the absolute minimum. And now, is there an absolute maximum? Well, there is not, because as you can see, this is going to go and grow forever in both directions. So there's only an absolute minimum, but no absolute maximum. And then just for the sake of thoroughness, I should point out that since this is an absolute minimum, it is also a local minimum. Let me write that on this side. So there is no local minimum. Excuse me, there is no local max. So the key concept I want you to get here is that every absolute minimum or absolute maximum is a local minimum or max, respectively. All right, let's look at the next one. So I'm back here on GeoGebra, and I'm going to go ahead and type in y equals, and I want to use the cube root, but if you notice, there's a square root right there, but there's no cube root. So we're going to use this option here for an exponent. So I want x, and then the exponent I want is the 1/3 power. Okay, so as you can see here, I have a graph of y equals the cube root of x. So now would be a good time to review the fact that absolute extrema depends on the interval. So without an interval, we don't need to test the endpoints, but if we restrict the interval, we do need to test the endpoints. So for this example, let's look at this on two intervals. The first one, of course, is going to be from infinity to negative infinity to infinity. On this interval, I don't have an absolute maximum since it keeps going. I don't have an absolute minimum. And in fact, there's no local mins or maxes either. There's no ups and downs here to give us local mins and maxes. So there are no absolute min, no local min, no absolute max, no local max. Okay, so now let's look at this on a different interval. What if I restricted my interval to a closed interval? from -1 to 1. And these are x values, FYI. And I'll use the same color here. That means our curve would stop here. That's it. And it would also stop here. So it'd be like all of this does not exist. So if we restrict the interval here, we suddenly do have an absolute minimum and an absolute maximum. Okay, you can see that I kind of moved things over to make some space, but now we do have an absolute minimum. It's right here. This is the absolute minimum point. So let's write that down. We have an absolute min located at x equals -1. As an ordered pair, that's at -1, -1. But I'll just leave it like this. This is also local. And we also have an absolute maximum here at x equals +1. And I just realized I did not scale this so that the values were more visible. So let me do that real quick. There we are. So we also have an absolute max at x equals 1. And this is also local. Okay, we have one more to examine. So let's go back to GeoGebra. And as you can see, here I am back in GeoGebra. And we're going to graph y equals the absolute value of x. Then I need to use the right arrow here to get out of that absolute value. So the absolute value of x minus x squared. There it is. It reminds me of the top of a heart. All right, so here is the graph. And on your own, would not need to see each one half. It would be enough to say, label and scale your graph in this manner. I just need to see some clear labels and a clear scale. And so what do I have here now? I have the graph of y equals the absolute value of x minus x squared. And so again, we can look at this from two intervals. Or actually, we can look at this from an infinite number of intervals. But for the sake of brevity, I'm only going to use two intervals. The first one again, let's look at the first interval. The interval we're going to use is again -infinity to infinity. So if we're looking at all the x values, as far out as we can go, this is going to keep getting smaller and smaller on the right and smaller on the left. In short, and I didn't do this for the other ones, but if you're looking at end behavior, you could say the limit as x approaches -infinity. For brevity's sake, again, I'll write f of x here, of f of x is equal to -infinity. And the same goes for the positive direction. So there's going to be no local minimum is what that tells me. Excuse me, no absolute minimum. Now, what about an absolute maximum? And actually, before we get to that, what about a local minimum? Do you see one? Because I do. All right, right here. Maybe you saw it right there. That is a local minimum because nearby the values of this function are larger than it. And really, if we look at our definition, here at 0, and we're still calling this f of 0 is smaller than or equal to f of x whenever x is near 0. So if x is near 0, f of 0 is definitely smaller than it all around here, almost all the way to 1. And actually, it still fits our definition at 1 and -1 because we can have equality. So that is a local minimum. Local minimum at x equals 0. And that tells us that this is the location along the x-axis of that minimum. All right, so now what about an absolute maximum? I see two of those actually, one here and one here. So absolute max here and here. So at x equals -1/2 and x equals +1/2. And so these are also local. So now let's take a look at this on a different interval. What if the interval I look at this on is from -1 to 2? So these are the restrictions on x from -1 to 2. So that would be from here to here. And let's go ahead and sketch in these endpoints. And I'll use this green color here just to make that clear. So these are x restrictions. So that means we'd have a closed dot here and then a closed dot here. And our curve would only live within this interval. Now I do see an absolute minimum. We have an absolute minimum at x equals 2. So that would be right here, because on this interval, if I'm only considering this portion that I'm highlighting in red currently and not considering anything else, then I do have an absolute minimum. That is also a local minimum. But we have more local minimums. This is still a local minimum, and now this is also a local minimum. So let's go ahead and write that down. There is a local minimum at x equals -1 here, and again, I'm restricting to this portion, and I may as well just highlight it in green so that we don't lose our restriction. So if we're just considering this restricted highlighted green graph, then we also have a local minimum at -1, at x equals 0, and at x equals 2. What about absolute? Absolute max. Those are still the same at x equals 1/2 and x equals -1/2. These are also local maximums. Okay, so just to recap some key points here, absolute minimums and maximums. These are also local minimums and maximums. It doesn't go the other way around. If we have a local minimum, it's certainly not an absolute maximum. As you can see here, this is a local minimum. And on this interval, it is not an absolute minimum. Even on this interval, it is not an absolute minimum. Next, extrema is dependent on both the function and the interval. And I haven't written that down, so let me make some space to write that down. So again, extrema are dependent on function and interval. It doesn't matter if this function has these absolute maximums here. If I don't restrict the interval, then it's not going to have an absolute minimum. So please take these key points with you.